Welcome back to AI from Zero to Researcher. This is episode 8, Attention and Self-Attention. Last time, we watched an RNN try to translate a sentence and struggle because every piece of information had to squeeze through a single fixed-size vector. That bottleneck was the central failure of older sequence models. Today, we remove it, and the tool that does it is attention. If the encoder-decoder bottleneck from episode 7 feels fuzzy, go back and revisit it before continuing. Everything today builds directly on that failure. What if, instead of squeezing everything through one vector, the model could look back at every previous position and decide what's relevant? That's attention. And the math is simpler than you'd think. Here is the core promise. Instead of hoping that information survives a chain of hidden states, attention lets the model directly ask which earlier positions matter for the thing I'm computing right now, and get a weighted answer. No chain, no bottleneck. Just a direct query across the entire sequence. And notice something. This idea of a weighted combination should sound familiar. Back in episode 2, we defined a neuron as a weighted sum plus a bias plus an activation. Attention is also a weighted sum, but now the weights themselves are computed dynamically from the data. The model learns not just what to combine, but how much of each thing to use, and that recipe changes with every input. Here is another way to think about it. Imagine you have a phone with hundreds of contacts, and someone asks you about a friend. The RNN approach is like scrolling through every contact from the beginning, hoping you remember the right one by the time you reach the end. Attention is like typing a name into the search bar and jumping directly to who matters. Let's build the intuition before touching any math. Consider the sentence. The cat sat because it was tired. When the model processes the word it needs to figure out what it refers to. In an RNN, the model would have to hope that information about cat survived being passed through sat and because. That is fragile. With attention, the model at position, it can look directly at every other position and compute a relevance score. How related is it to cat? To sat? Those scores become weights. The model then takes a weighted combination of the information at every position using those weights. If cat gets a high weight, most of the information flowing into the representation of it comes from cat. That is the entire idea. Everything else is the specific mechanism for computing those relevant scores. Now the mechanism. Attention uses 3 ingredients: queries, keys, and values. These are not metaphors. They are concrete linear projections, 3 different weight matrices applied to the same input embeddings. Here is how to think about each one. Think of it like ordering food. You walk in and say, "I want something spicy." That is your query. Each dish on the menu has a label: spicy, sweet, savory. Those are the keys. When your query matches a key, you get served the actual dish. That is the value. Now let's see how this works with actual math. The query is what the current position is looking for. When the model processes it, the query encodes, I need to find my referent. The key is what each position advertises about itself. The key for cat encodes, I am a noun, a subject, an entity. The value is the actual information that gets passed along. If the query key match is strong, the value is what gets retrieved. Concretely, for each position I in the sequence, Q sub I equals X sub I times WQ. K sub I equals X sub I times WK. V sub I equals X sub I times WV, where WQ, WK, and WV are learned parameter matrices. The model learns, through training, what to put into queries, what to put into keys, and what to put into values. These are not hand-designed. They emerge from gradient descent on the task. Why 3 separate projections instead of just using the raw embeddings? Because the model needs different views of the same token for different purposes. What makes a token a good match, key, is not the same as what information that token should contribute, value. Separating them gives the model more flexibility. There are 2 main flavors of attention, and the difference is simply where Q, K, and V come from. Self-attention, Q, K, and V all come from the same sequence. Each position attends to every other position in its own sequence. This is how a language model lets every word incorporate context from every other word. Cross-attention. Q comes from one sequence, while K and V come from a different sequence. This is how a translation decoder attends to the encoded source sentence. The decoder asks, which parts of the French input are relevant to the English word I'm generating right now? In self-attention, the model is asking, what context within my own input is relevant here? In cross-attention, the model is asking, what information from that other source is relevant here? Both use exactly the same math. The only difference is where the matrices come from. Now, a research habit that will serve you well. When you see an attention heat map, like a grid showing that it attends strongly to cat, it is tempting to say the model understands that it refers to cat. Be careful. Attention weights show where the model routes information. They do not tell you why, and they do not tell you the full story. A token might receive a high attention weight for syntactic reasons, not semantic ones. Multiple layers of attention interact in complex ways, and attention is only one of many operations inside a model. The feed-forward layers, residual connections, and layer normalization all contribute to the final output. Research has shown that attention weights can sometimes be rearranged significantly without changing the model's predictions. This does not mean attention maps are useless. They are informative evidence. But they are not a complete explanation of the model's reasoning. The research habit: be cautious when turning internal signals into explanatory stories. Evidence is not explanation. Correlation in the weights is not causation in the model's behavior. Let's implement single-head attention from scratch. No frameworks. Just NumPy. The word it attends most strongly to cat, Kone 0.43. With random untrained projections, this is a coincidence of the initial weights, not learned behavior. But it shows exactly how the mechanism works. The query for it happened to align with the key for cat more than with other keys. In a real trained model, these projections would be shaped by billions of training examples, and the attention patterns would reflect genuine linguistic relationships rather than random alignment. Each row sums to 1 because softmax produces a probability distribution. Each row tells us, when computing the output for this token, what fraction of information comes from each position. For it, 40% comes from cat, 25% from sat, 20% from itself, and 15% from the. The output for each token is then a weighted blend of the value vectors, mixed according to these weights. That blended vector replaces the original embedding and gets passed to the next layer. Time for the what-if experiment. What happens if we remove the scaling factor? Think of the scaling factor as a temperature dial. Turn it off, and attention becomes a spotlight, blinding focus on one token, darkness everywhere else. Keep it on, and attention becomes a lantern, spreading light across everything that matters. See the difference. The difference. Without scaling, the weights become much more extreme. It now puts 57% of its weight on cat, up from 40%, and the distribution is sharper overall. V puts 66% on it instead of a more even spread. The distribution is approaching 1 hot. Nearly all the attention goes to a single token. Why does this matter? Because when softmax outputs are nearly 1 hot, the gradients for the low-weight positions become vanishingly small. The model stops learning from those positions. It becomes rigid, unable to update the relationships it has already formed. With higher dimensional embeddings, the problem gets worse. If dk equals 512 instead of 4, the raw dot products are much larger, and the softmax outputs become even more extreme. Small details in math have big consequences. That single division by square root of dk is the difference between a model that learns flexibly and one that collapses into rigid, brittle attention patterns. Before we wrap up, let's watch the entire mechanism work on one token from start to finish. We start with the word it, just a vector of numbers. 3 projections split it into a query, a key, and a value. The query fans out and compares against every key in the sequence by a dot products. The scores get scaled down by the square root of dk to prevent extreme values. Softmax converts them into a probability distribution, how much to attend to each position. Finally, we blend all the value vectors using those weights. The result is a new, context-enriched representation that replaces the original embedding of it and flows to the next layer. Let's compress what we covered. Attention is a mechanism that computes context-dependent weighted sums. Each position gets to look at all positions and decide how much information to pull from each one. The mechanism uses 3 projections: queries, what am I looking for? Keys, what do I offer? And values, what information do I carry? Queries match against keys via dot products. Those scores are scaled by square root of dk, passed through softmax, and used to weight the values. Self-attention applies this within a single sequence. Cross-attention applies it between 2 sequences. Attention weights are evidence, not explanation. Do not overinterpret them. And the entire equation is attention of q, k, v equals softmax of q times k, transpose over square root of dk times v. Or operations. That is the conceptual heart of modern AI. In episode 9, we take this attention mechanism and assemble it into the full transformer architecture. We will split attention into multiple heads that learn different relationship types in parallel. We will add positional encodings so the model knows word order. We will stack these blocks and connect them with residual paths and normalization. And we will see the 2 major training objectives, masked language modeling and next token prediction, that turn transformers into the foundation of modern language models. Here is a question to carry forward. We showed that a single attention head computes 1 set of relevance weights. But relevance is not one-dimensional. The word cat is relevant to it for coreference, but sat is relevant to cat for syntactic structure. What happens if we run multiple attention heads in parallel, each learning a different notion of relevance? That is where episode 9 begins.